Good day and welcome back to the fifth part of our discussion of double integrals over general regions. And one of the ways we are going to be asking questions now and also in our upcoming material will be to ask you to find the volume of some solid which we describe. So in this case it's going to be the solid enclosed by the three surfaces y equals x squared, z equals 3y, and z equals 2 plus y. And oftentimes difficulty, and in this problem I think the main difficulty, might be associated with visualizing what this solid looks like. So let's first get a few kind of key words out here. So z equals 3y represents a plane, as does z equals 2 plus y. But I'd like you to think for a moment, what word would you use to describe y equals x squared? And if we go back to our discussion on quadric surfaces, whether it looks like it or not, this y equals x squared is something that we would call a parabolic cylinder. And the cylinder is really the key word associated with this surface. So I'm going to go ahead and try to sketch roughly what this will look like. And sometimes my suggestion is going to be less can be more. If I try to do an extremely accurate sketch and get everything included, we wouldn't be able to see what's going on. But if we were maybe just to represent the two planes by lines, say their x equals 0 trace, along with portions of this cylinder, we might get a better picture or be able to better visualize the solid. My other bit of intuition is that the two planes z equals 3y and z equals 2 plus y, those are going to bound the surface, or the solid I should say, in the z direction. And then along with that, y equals x squared will help determine d, where d is going to correspond here to our region of integration for the double integral. So let's go ahead and see if we can represent these two planes. If we first focus in on z equals 3y, and specifically the x equals 0 trace, that would be flat in the screen in the yz plane. That x equals 0 trace would be a line going through the origin with slope 3. So roughly speaking, without indicating really any scale, I'm going to say this is z equals 3y. Similarly, if we wanted to visualize the second plane, z equals 2 plus y, we can think of that in the x equals 0 trace as a line with z-intercept 2 and slope 1. So if we add a little bit of scale now to the z-axis, it will intersect the z-axis at 2, and it will have slope 1. So it will very quickly be overtaken by that first plane. And in fact, we could even note precisely that point of intersection corresponding to the two planes. For example, in this x equals 0 trace, so 0 for the x value, they intersect exactly when y is 1 and z is 3. So an observation that we can make is that the two planes z equals 3y and z equals 2 plus y intersect when y is equal to 1 and z is equal to 3. Because remember, to visualize these planes, we just drag the lines we've drawn in that direction parallel to the x-axis, and that point of intersection is going to end up forming a line of intersection. And if you go back to our previous notes, you will find examples where we actually calculated out these lines of intersection. Now, in order to get this parabolic cylinder involved, I'm going to sketch the z equals 0 trace, so in that xy plane, which is simply a parabola that opens up in the direction of the positive y-axis and it has its vertex at the origin. And now we have kind of the difficult part of the problem, I think, combining this all together. Our solid is going to be bounded between the two planes, and it's going to lie somehow inside this cylinder. And note we observed a moment ago that the planes intersect along this line, y equals 1. So how I'm envisioning this is we have this region D in the xy plane, and the solid is bounded between the two planes. Z equals 3y is the lower one, z equals 2 plus y is the higher one, sitting above that region D. And I realize this is a difficult thing to see, so before going any further, let me throw a GeoGebra video in here as well. Alright, so I've hit play in this video. The first plane that we see is z equals 3y. Then secondly, we have the plane z equals 2 plus y. And we can kind of see, and I've paused it, it goes through that z-axis at 2, and they're intersecting along this line, which corresponds to y is 1 and z is 3. And just to see that a bit more clearly, let's add in that plane y equals 1. So we see the intersection. And also it's worth noting that we can see in the video, this region or volume bounded between the two planes. Now we also need to get the cylinder y equals x squared in the picture. And just to rotate this around now to give kind of a bird's eye type of view, and removing everything from the picture, we can now see the region D that we had previously indicated. So inside this parabola, y equals x squared, and below that line, y equals 1. And hopefully this helps give you a little bit of intuition as to what this solid will look like, and also remind you that you do have this tool at your disposal. GeoGebra is a freely available program where you can enter in these surfaces and very quickly and efficiently visualize what is going on. So now that we've developed a bit more intuition in terms of what this solid looks like, let's go ahead and write down a double integral that will calculate its volume. And note that we've sketched separately this region D in the xy plane, and whatever our region of integration is for the double integral, I will request that you always include a picture of that. And how we set up this integral is we take the larger curve minus the smaller. And in this case it would be the larger surface, 2 plus y, minus the smaller surface, 3y. And note we can clearly see above, 3y is the smaller, 2 plus y is the larger. So we think we take the larger minus the smaller, just like we did when we were in Calculus 1 and finding areas between curves. So our integrand simplifies very nicely. We have 2 minus 2y. What we need to do now is turn this into an iterated integral that we can evaluate. And looking at the line y equals 1, we know the points of intersection with the parabola y equals x squared. They intersect precisely when x is minus 1 and 1. And you could view this as either one of these type 1 or type 2 regions, but I think most conveniently we can think of it as a type 1 region, where on the outside we have the x values varying from minus 1 to 1, and if you pick your favorite value of x between minus 1 and 1, the y values vary along these vertical lines, going from the smaller curve, y equals x squared, to the larger curve, y equals 1. And getting the problem down to this point is, I think, most definitely the biggest difficulty associated with this problem. And many times what I'll do is when we get here, I'll say for good practice, I will let you finish the evaluation. And when you do that, note my optimism, you should get back 16 over 15. So just a reminder, when it comes to finding volumes enclosed by surfaces, we go back to this geometric interpretation of the double integral, calculating a net difference of enclosed volumes. Maybe the most difficult part associated with this problem is the visualization, so make sure to spend some time practicing, and also don't be afraid to use the tools that you have at hand. That is this wonderful program, GeoGebra. And also, my office hours and contacting me via email. So in the next video, we'll look at a few more examples related to switching around the order of integration, which can also be a difficulty. So stay tuned and take care.